great pleasure to welcome Professor Yacine Ali-Haïmoud for this week's ITC Colloquium. So Yacine did his undergraduate studies in France before then moving to the United States, where he did his PhD at Caltech, and then was a series of eastward migrations as he then went to the IAS for a postdoc, then at Johns Hopkins for a postdoc, and then finally moved to NYU a little over 2 years ago, where he started as an assistant professor. So Yacine works on quite a myriad range of topics, ranging from 21 centimeter to the CMB, to dark matter, to primordial black holes, and everything else you'll hear about in the next 45 to 50 minutes. 55 minutes, who knows how long, okay. But I'll let Yacine take the floor. Thank you.
Thank you very much for inviting me. I think the last time I gave a talk here was 9 years ago, so I'm glad to be back. All right. So I don't think I need to give a long introduction to dark matter. Probably lots of people know much more about it than I do. So the executive summary is that dark matter is some stuff that does not seem to absorb, emit, or interact with luminous matter, at least within observational bounds, and manifests itself across a very broad range of scales, from dwarf galaxies to clusters of galaxies, and all the way to the largest gigaparsec scales of large-scale structure in the universe. And to even larger scales, dark matter manifests itself in the cosmic microwave background anisotropies, from which we have been able to infer the abundance of dark matter, whatever that is, to basically percent level precision. So candidates for dark matter include, very broadly speaking, it could be some kind of new particle. We already have a bunch of particles in the stellar model, the quarks, leptons, gauge force carriers, the Higgs, and so why not have another additional particle? This is, as I said, a very broad class of candidates, so one of the things I'll talk about in this talk is to ask whether, if dark matter is some new particle, whether it can interact, whether we can detect its non-gravitational interactions, in particular scattering with standard model particles, through cosmological probes. Another broad class of candidates would be that dark matter could be some kind of compact object, macroscopic compact object, and for example, could be in the form of primordial black holes. This is actually a very old idea put forward by Stephen Hawking in the early 70s, and I'll talk a little bit more about this, but the idea, this is my own artist impression, is that if you have in the early universe on small enough scales some sufficiently large overdensities, they could directly collapse and form black holes much before forming the first stars. So they're primordial in the sense that they're not astrophysical, they don't result from the death of massive stars. So the plan of this talk will be, first, I'm going to go briefly review in pictures the physics behind the cosmic microwave background. And then I will tell you a little bit about how one can probe interactions of dark matter if it was some kind of particle that can scatter with baryons, for example, with the CMB. And in the third part, I will tell you about primordial black holes, both their signatures in the cosmic microwave background and in gravitational waves. Let's start with a very brief overview of the CMB. I don't know why it's doing this. All right. So just to set the language first, what one measures when one measures the cosmic microwave background is some total intensity, but you can define the temperature out of this. Very generally, it doesn't have to be a blackbody spectrum, but you can inverse this function to define the temperature. So this temperature is some mean temperature plus some fluctuations that only depend on the spatial direction, which I will call anisotropies, plus some uniform, spatially uniform, but frequency-dependent piece, which we call spectral distortions. Plus, you could also have some mixture, which I will not talk about, some spatial spectral distortions, for example, the Sunyaev-Zel'dovich effect. So I will talk both about spectral distortions and anisotropies. All right, what are the protagonists in the story? So we're going to start the story after Big Bang nucleosynthesis. So what we call baryons are electrons, sorry for the particle theorists, protons and helium nuclei, something with an abundance of something like 8 helium nuclei per 100 hydrogen nuclei. We have a bunch of photons, something like a few billion photons per baryon. A bunch of neutrinos and antineutrinos, almost as abundant in number as photons, and whatever the dark matter is. All of those are interacting through gravity, and photons and baryons, I don't know what is doing this, are tightly coupled for the first 400,000 years through Thomson scattering. So for the first 2 months in the history of the universe, photons are very easily created and destroyed, and they're also very easily thermalized in the sense that they can easily change their energy through interactions with baryons. So what this implies is that no matter what happens in the first 2 months of the history of the universe, the frequency spectrum of the CMB is that of a blackbody spectrum. If, however, after 2 months, some process can inject or absorb energy from the photon baryon plasma, this would lead to a distortion of the cosmic microwave background, i.e. a change away from the Bose-Einstein blackbody spectrum.
First 2 months that is special.
The first 2 months is because after that, photon creation and destruction processes such as free Bremsstrahlung and double Compton scattering are no longer as efficient. So the density becomes low enough, and you can no longer efficiently create photons, for example, from Bremsstrahlung radiation. So you can still thermalize, you can still change efficiently the energy of photons, but not their number. So if you inject energy, you would get some non-zero chemical potential. I cannot derive exactly 2 months within a few seconds, but I can point you to the correct references. So what the data say, and this data is now almost 3 decades old, 2.5 decades old, from the Kobe satellite, is that the cosmic microwave background is a perfect blackbody within 1 part in 10,000. Okay? So what this tells us is that nothing has too dramatically either heated or cooled the photon baryon plasma after the first 2 months in the history of the universe. And several people are talking about going beyond this almost 30-year-old results. And so it is, in principle, technologically feasible to improve the sensitivity by as much as 4 orders of magnitude. For example, Kogut et al. Proposed the PIXI concept to measure spectral distortion to much better precision. So that was for the spectral distortion part, just to set the picture. So then we move on to CMB anisotropies. And so one very important process in CMB anisotropies is the cosmological recombination process. So the idea is that as the universe expands and cools down and becomes less dense, it goes from being a fully ionized plasma to neutral gas. And this proceeds in several steps. First, helium captures its first electron, then a second electron, and around a few 100,000 years after the Big Bang, hydrogen captures its lone electron and becomes neutral. This free electron fraction, just for reference, is normalized to the total number of hydrogen atoms, which is why it starts at 1.16, because you have 8 helium nuclei per 100 hydrogen atoms. Okay, so why does this matter? As time goes forward, temperature decreases. You start with this ionized plasma, and then it becomes mostly neutral. Photons efficiently Compton scatter off the free electrons, and once the plasma becomes neutral, photons can finally scatter one last time and propagate freely. They do this around the last scattering epoch of 200,000 years after the Big Bang. Just to put this in a bigger context, this happens early on in the history of the universe, and these photons propagate through first stars, first galaxies, etc., all the way to today. And just in case this is mostly for the students, if you haven't thought about this much, this, of course, is the same in every direction, which is why one sees the cosmic microwave background. Even if we're not at the center of the universe, we're at the center of our observable universe, and we see this sphere, this epoch of last scattering, appears as a surface of last scattering, as seen from our point of view. So what are we seeing exactly? So this big blob here is the emission from our own galaxy in the microwaves, dust emission, synchrotron radiation, etc. But if you remove this, what exactly are you seeing? So before 400,000 years, when photons efficiently scatter off free electrons, photons and baryons are tightly coupled. So together, so the photons provide a lot of pressure because they're relativistic, and baryons provide containment for the photons, so they impede their free streaming. So together, these two form an ideal fluid with a large pressure. Now, if you if you put in some small overdensity in the initial condition, I'm here putting some very idealized overdensity, and Daniel has probably much better plots than this, but I've tried to make one only in Mathematica. So if you have over density and you have a fluid with a high pressure, this will launch a sound wave, and this sound wave will propagate for about 400,000 years, up until the moment where photons are no longer contained with baryons, and then they freely propagate. Now in practice, you don't have these isolated over densities, you have superposition of many random over densities with some power spectrum, and so what really happens is that you have some random superposition of sound waves which oscillate for about 400,000 years. And what you see in the cosmic microwave background is essentially a snapshot of this last oscillation. All right, so what one measures is the temperature and polarization also of the cosmic microwave background, and the quantitative thing that is extracted is the power spectrum, which is the variance of either the temperature or the polarization fluctuations as a function of angular scale. So here, angular scale, small scales goes to the right and large scales go to the left. This is just the harmonic transform of the CMB power spectrum. And so this data is very well fit by a rather simple, conceptually simple model with only 6 parameters. One of the parameters being, for example, how much dark matter there is. And so if you try to make the universe having less dark matter, you see that the fit goes quite horribly wrong, and you do need to have this rather precisely measured abundance of dark matter. And for, as an aside, I asked a colleague of mine, Kimberly Body, if she could try to run Monte Carlo analysis with no dark matter at all, and what would the fit look like, and the answer is that it just doesn't converge. So, all right. So one thing I want to emphasize is that